Hello and welcome to my video. Today we are going to handle the equation, and actually we are going to prove the existence of the real root of this specific equation. And in the process we are going to use two famous theorems in mathematical analysis. So the problem says, for any natural number n, prove that this equation has a real root in the open interval 0, 1. So like I said, there exist two theorems that we can use to prove the existence of the root of this equation. Some of you may encounter these in high school calculus or in a freshman year of college. In this first method, I am going to use the intermediate value theorem. The theorem itself is like this. Consider a function fx that is continuous on the closed interval a, b, like this, and let k be an arbitrary number between fa and fb, the y values at two endpoints of the interval. Then there exists a number c in the open interval a, b such that fc equals k. So this is the intermediate value theorem. I am not going to prove this theorem because it requires some knowledge from college level analysis. So we are just going to intuitively understand this theorem and move on. For our problem, let this left-hand side of the equation be a function, specifically function fx. First, we must check the condition for the intermediate value theorem, the continuity of the function. In this case, fx is definitely continuous on closed interval 0, 1. Moreover, f0 is simply 1, so it is a positive value, and f1 is 1 minus 2 plus 3 minus 4 plus 2n minus 1 minus 2n. We have even number of terms, so let us group with two terms. Then we have minus 1 here, and minus 1 here, and minus 1 here. So we have total n minus 1s. So this is minus n, which is a negative number. So f0 is a positive number and f1 is a negative number. Therefore, 0 is the number between f0 and f1. More specifically, it is greater than f1 and less than f0. Therefore, by the intermediate value theorem, there exists a number c in the open interval 0, 1 such that fc equals 0, which means that the given equation fx equals 0 has a real root in the interval 0, 1. And this completes the proof. The second method is using Rolle's theorem, which is the basic property related to the derivative of the function. That is, this is the theorem applicable to differentiable functions. So the theorem is, if a function f is continuous on the closed interval a, b, differentiable on the open interval a, b, and fa equals fb, so like this, the function has the same value at x equals a and x equals b, then there exists a number c in the open interval a, b such that f prime c equals 0. So there exists a point c where the value of derivative becomes 0 at that point. So how can we use this theorem in our equation? The Rolle's theorem is the theorem of existence of point where the derivative is 0, so we want our predefined function fx to be the derivative of another function. Therefore, let us integrate fx and see what we get. So we have x minus, and the next term becomes x squared, and then we have x cubed and x to the 4, all the way up to x to the power of 2n minus 1 minus x to the power of 2n. And of course plus c. Here the value of constant c really doesn't matter, so let's just take the simplest one and define gx as the above function with c equals 0. Now let's check some conditions. Gx is a polynomial function, so it is indeed continuous on the closed interval 0, 1 and differentiable on the open interval 0, 1. Moreover, g0 is obviously 0 and g1 is 1 minus 1 plus 1 minus 1 plus, and we have even number of terms, so we have 1 minus 1, which is also 0. Therefore, by the Rolle's theorem, there exists number c in the open interval 0, 1 such that g prime c equals 0. And since the derivative of gx is simply fx, it means that the given equation indeed has at least one real root in the open interval 0, 1. So here we have another proof. And that's all I prepared for this video. This so-called relation between roots of the equations and the functions is actually quite important topic, so perhaps you will see me making many more videos on that topic. If you do not want to miss those, please subscribe to my channel for more math videos, and I will see you in another video.